Hello everyone, welcome on our YouTube channel Physics Made Easy Kota. In this lecture, we are going to study about the chapter Current Electricity. In this chapter, we will discuss some common concepts regarding electricity and the current. In electrostatics, we have discussed that the charges are at rest. But in this video, we are going to learn about the motion of the charges. Electric current can take place in the solid, liquid and gases, that there is a passage of the current through all these different states of the matter, and these passage is only possible due to the current carriers. These current carriers take place in the solid, also in a liquid and gases. For the current carriers in solid like conductors, for example, we can take the solid as a copper, metal, silver metal. The free electrons constitute an electric current. Electrons in the outermost shell of the atom, which are known as the valence electrons in a conductor, are free electrons as they do not bound to any atom. These electrons are free, so they can move in the whole conductor just like the gas molecules in a conductor. But under the effect of the external electric field, these free electrons move in a particular direction, that is in the direction opposite to the direction of the external electric field, and in this way the electric current formation take place. So we can say that the free electrons or the valence electrons are the current carriers. Due to the formation of these, there is a formation of the electric current. But in case of the insulators, all the electrons are tightly bound to the nuclei of their parent atom. Hence, they do not have any free electrons and there are no current carriers in a practical way in an inductor. Now for the liquids. Some liquids which allow electric current to pass through them and they finally dissociate into ions are called electrolytes. For example, copper sulfate solution, NaCl solution. These electrolytes dissociate into positive and negative ions, and under the influence of the external electric field, the positive and the negative ions of the electrolyte move in a definite direction to form the electric current. Thus, positive and negative ions are the current carriers in the liquids, due to which electric current set up in the liquid. So now, who is a current carrier in our gases? We know that generally gases behave as insulator of electricity, but they get ionized and become conductor at a specific conditions, like at a low pressure when the potential difference applied is high across them. Then the ionized gas contain the positive ions and the electrons. Thus, these positive ions and electrons are the current carrier in gases. So current carriers form the electric current, and electric current is defined as the amount of electric charges flowing through any cross section of a conductor per unit time, and the direction of the flow of the positive charge through a material give the direction of the electric current. This current is also known as a conventional current. There is a story for calling it as a conventional current because in the beginning, that is before the invention of the electron, it was thought that electric current is due to the flow of the positive charges. However, in a conductor, the flow of the electrons which are having the negative charge make up the electric current. So the direction of the flow of the electron is always opposite to the direction of the conventional current. Thus, direction of electric current in a conductor is taken as the opposite to the direction of the flow of the free electrons. There is a complete mechanism for the flow of the electric current in a conductor, as every matter is made up of atoms and molecules that we already aware. In a solid conductor, atoms are closely packed and the valence electron of an atom are not attached firmly to its nucleus. So these valence electrons are free to move throughout the volume of a solid conductor even at a room temperature. So they are free to move and therefore they are known as the free electrons. So in a conductor, the free electrons move randomly with a thermal speed that must of the order of the 10 raised to power 5 to 10 raised to power 6 meter per second, and all these things are taken place at a room temperature. In the figure, the diagram shows about the motion of the electrons and also the direction of the conventional current. So we assume this conductor, and we can take a very small portion of this conductor, and we assume that the flow of the electrons is such a way that the number of the electrons crossing through a given cross section of a conductor in any direction is equal to the number of the electron crossing through that cross section of a conductor in the opposite direction. In other words, we can say that from the same cross sectional area the electrons pass through for the travel time. So the net flow of the electron can be taken as a zero. Hence, electric current in a conductor is zero. So this figure explains the random flow of the electrons in the conductor, and the net electric current in the conductor is taken as zero. Now we take the case of the electric field. When there is the application of the electric field, then how the free electrons behave. You can see in the figure the symbol E denotes the direction of the electric field, and due to the electric field the free electrons experience a force, but this force is in the opposite direction, so their motion is towards the opposite direction to the direction of the electric field. They start accelerating, but their acceleration becomes zero, because when electrons collide with the ions in the solid, their acceleration goes on decreasing and it becomes zero. But they are under the influence of the electric field, again they try to accelerate, and in this way this process continues, and therefore the free electrons drift in the direction opposite to the direction of applied electric field. So we can say that electric current in a conductor is due to the drift motion of electrons in the direction opposite to the direction of the applied electric field. If the cell or a battery is disconnected, then the electric current immediately stops. So the electric current exists only for the duration. When there is a connection of a cell or a battery, then of course then there will be the electric field across a conductor. When the cell or a battery connected across the end of the conductor, only then the electric field is set up and the current formation take place. In the mechanism, the word drift is very important as the electrons get drifted. So what is the drift velocity of electrons? It is the average velocity with which free electrons in a conductor get drifted in a direction opposite to the direction of the applied electric field. So this is one of the most important knowledge, that there are the different types of the electric current. The first one is a DC current, which is also known as a direct current. DC current is of two types. One is a steady direct current, in which the magnitude and the direction of the current do not change with time. Another one is a variable direct current, in which the magnitude of a current changes with time but the polarity remains same. The second type is the alternating current, which is known as a AC current. An electric current is said to be alternating current if its magnitude changes with time and polarity reverse periodically, means after regular interval of time. Thank you for watching our video. We meet in the next part, that is a part number 2 regarding this chapter. Take care. Have a nice day.